Hi, in this video, we are going to cover 3.2 polynomial functions and their graphs. However, I am going to split this up into two videos. And in this first video, we are going to take a look at the end behavior of these polynomials. Okay, so 3.2. Polynomials, polynomial functions, and their graphs. So we are going to be looking at polynomials of degree n. So we saw degree 2 polynomials in the previous section, which are quadratics. Okay, so let's take a look at the very first kind of polynomial you played around with, and that would be the line. So it may have not looked like this when you first learned it. Maybe you looked at it as y equals mx plus b. Whatever you call the letters, it still has the same structure. So this one here is the line, the linear graph. And then we looked at degree 2, which is the quadratic. And that one looks like this, ax squared plus bx plus c. So we know what that looks like. So what we're going to be doing here in 3.2 is looking at higher degrees, not just degree 2, but degree 3. So that would look like this, degree 3. And the degree 3 is called a cubic polynomial. And we will also look at degree 4. So ax to the 4th. So this here, degree 4, is called a quartic. And degree 5, we will also probably look at the degree 5 is called a quintic. And then everything else beyond that is just no special names. Okay. And we can keep on going. Ax to the 6th, ax to the 7th, 8th, 9th, higher degree polynomials. Okay. So everything else we just call higher degree polynomials. These are all higher degree polynomials, but they also have very specific names, the quadratic, cubic, quartic, quintic. Okay. So let's take a look at a very general polynomial. So suppose that I have this, and if I use all the letters, then I can only use the alphabet, 26 letters, right? And then I would run out. So I'm just going to call them all A's, but instead of like A, B, C, D, E, F, I'll say A. I'll call one of them A0, and then A1, A2, A3. That way I never run out of variables. Okay, so I'm going to call this AN. And then the next one is going to be smaller. And the next one's going to be even smaller. Don't worry if you're looking at this and it looks a little intimidating with all these numbers and letters and subscripts and whatnot. Okay. I need it for structure so I can show you what part of any polynomial I'm talking about. Okay, so if it's in order, just like the ones above are all in order from degree, from exponent, like that last one, 5, 4, 3, 2, 1, and no x. Okay, so if it's in order, then this very first term here is called the leading term. And the number an is the leading coefficient. So this leading term and this leading coefficient will play an important role in this entire chapter. Okay. And you'll notice that they all have a variable x next to them, except for this one here at the end. This one doesn't have a variable, so this here is the constant. Okay. All right, so you might be asked to identify all these different characteristics of a polynomial. So, for example, suppose that you're given this polynomial 3x to the 5th plus 4x to the 4th minus 3x cubed plus 2x squared minus x minus 7. Okay? It's in descending order. It starts with power of 5, and then it goes in order: power 4, power 3, power 2, power 1, and power 0. Okay, so you might be asked, okay, identify the leading term. So here, the leading term would be all of this here, including that sign, which is positive 3x to the 5th. Okay. You might also be asked to find the leading coefficient. So here, the leading coefficient would be the coefficient in the leading term. In this case, it would be positive 3. Okay. You might be asked to find the degree of this polynomial. So that's just the highest exponent here. Okay. So that would be this 5 over here. Okay. So this is a degree 5 polynomial. You might be asked to identify the constant. So that would be this over here, including that negative. Okay. So your constant is negative 7. And then it might ask you to identify all the coefficients. So that would be all the numbers. Okay, so that would be 3, positive 4, negative 3, 2, negative 1, and negative 7. Okay. All right, so those are just sort of the basic parts of a polynomial function. When we start graphing, we really only need to pay attention to the leading term and then all the zeros, which are the solutions to the polynomial. Okay, so graphing basic polynomials. Okay, so graphing basic polynomials. So what we look at is we usually have even exponents, even degrees, and odd degrees. Okay, so if we have just x, nothing added to it, nothing subtracted to it, nothing multiplied to it, Okay, and you have an even exponent, like you have x squared or x to the fourth or x to the sixth. Okay, but this exponent is an even number. Okay, so if you have x to an even number and that's all you have, then what happens is you have the graph of a parabola every single time. The only difference is that as that even exponent gets larger, your parabola gets a little more flat at the origin. Okay, so we know what x squared looks like. Okay, so we know that this is x squared. Okay, and what happens is if we go higher, like let's say we go with x to the fourth, I'll do that one in red. If you do x to the fourth, then it just gets a little bit wider down here. Okay, and if you do x to the sixth, do that one in yellow, it gets even flatter around here. Okay. And I can keep going. X to the eighth, it would be even flatter. So right around the origin, it just sort of looks a little flat. Okay. And then the same thing with odd exponents. Okay. So if we have f of x equals x to an odd exponent, like x to the third or x to the fifth, x to the seventh power, and nothing added, nothing multiplied, nothing subtracted. All you have is just that x, and you have this odd number exponent. Then here, in this particular case, then you will have the graph of x cubed, which we know looks like this, x cubed. Okay, so this is the graph of x cubed. And then what happens is, same idea over here. If we do x to the fifth, then right around here, it starts to flatten out. Okay, so this one is x to the fifth. And if we do x to the seventh, again, it flattens out right around the origin. So right there, right around the origin is where it starts to get kind of flat. Okay, and we can keep going. All right, so that's if you just have x to a power. If you have just x to an exponent, nothing added, nothing subtracted, nothing multiplied, then you will get one of these graphs. Okay, so that's not very interesting. So let's take a look at graphing other polynomials that look more like this one over here. Okay, where you have things that are added more than one term, and you have things that are being multiplied. Okay. All right, so in order to graph something like that other polynomial, we need to look at what's called the end behavior. Okay, so graphing other polynomials. Okay, so we need to look at the end behavior, and that's what we're going to focus on here in this video. And the other thing we need to look at are the zeros of the polynomial. Okay, and that's going to be in the second video. Okay, the zeros here are the x-intercepts. Okay, so when you guys are going to be graphing, you'll be looking at the end behavior, the left end and the right end behavior, you'll be looking at the zeros. And that's pretty much all that I will expect from you in order to do the graph. Okay. All right, so let's have a look at end behavior. Before we do that, let's have a look. You don't have to copy this part down. Okay, so this is just something, this is just a side. Okay, just pay attention. You don't have to copy this down. Now, if I have this, suppose that I have this here, 3x to the 5th power. And suppose that this here is my leading term of my polynomial. So suppose I have like 3x to the 5th plus, again, don't copy this down. Suppose I have all of this, 7x to the 4th minus 3x cubed minus 2x squared minus 9x plus 1. Okay, suppose that I have that, right? So what's going to happen is I want to pay attention just to that leading term. Okay, so I don't need any of these guys. Okay, so what's going to happen is I'm only going to take a look at that because that exponent is so high, and I'm going to be plugging in a very large x number that those other terms aren't even going to compare. Okay, it's not going to influence my result. Okay, so let's take a look at this, 3x to the 5th. Now, if I have a graph, right? So think of a number that's on this side of the graph. Okay, so maybe you're thinking 7, and maybe you're thinking 12. Okay, now give me a really big number that's on that side of the graph. Okay, so maybe now you're thinking 100 or 2,753. Okay, so those are big numbers. Okay, now let's go ahead and let's take a look at that number, 2,753. If I plug that in for x, 2,753 to the 5th power, I'm going to get a big answer, right? So the question is, am I going to get a big answer that's positive, or am I going to get a big answer that's negative? So hopefully you said you're going to get a very large positive answer, right? So if I choose an even bigger number than 2,753, like if I pick a number in the millions, right, or in the billions, am I going to get a very large positive answer or a very negative answer? So we will still get the same result. Okay, so this here is what we mean by the end behavior. So over here on the right end, what's going to end up happening is we're going to end up with bigger and bigger, bigger and bigger and bigger numbers the more we go to the far right. Okay. Now, let's go ahead and consider the left. So give me a number on the left-hand side, a very negative number. Okay, so maybe you're thinking negative 1,428. Okay, so if I plug that in, negative 1,428, and I raise that to the 5th power, then what sort of answer am I going to get? Am I going to get a very positive number or a very negative number? Well, I am going to get a very negative number, right? So here, what's going to happen on the left-hand side is that the more I go out on these negative numbers, then I'm going to end up with these answers that are going to be very, very negative. Okay, so this is what we mean by our end behavior. On the right-hand side, it would be going up, when we plug in these big positive numbers, we will also get big positive numbers. And when I plug in these very negative numbers, then we will also get these very negative numbers. Okay, so we can expect the graph to behave like that. Okay, so maybe the graph then looks like this, where on the right-hand side, it's going up, and on the left-hand side, it's going down. Okay, we don't know what it's going to look like because we haven't gotten that far. Okay, so, but that's the basic idea of end behavior and how we use the leading term to figure it out. Okay, so so let's go ahead and erase all of that. Okay. All right, so that was just an aside. Okay, so these are the things we need to look at when we're graphing polynomials. All right, so let's be more formal about end behavior. Okay, so end behavior, we are going to use the leading coefficient test, which I kind of just showed you. Okay, and what we do is we determine the right-hand behavior. I am going to be using RHB in the future, right-hand behavior. Okay. And so, again, right-hand behavior, the x's are positive. So replace x with a very large positive number. Okay. Positive result means up. Negative result means down. Okay. And then you're also going to do the same thing and determine the left-hand behavior. And what you do here is you replace the x with a very negative number. And again, positive result means up. Negative result means down. Okay, so Positive result means up. So that's like saying positive infinity, and down is negative infinity. Okay, goes down towards negative infinity, up is towards positive infinity. All right, so let's go ahead and take a look at some examples. Determine the end of behavior. Suppose I have this polynomial. P of x equals negative 2x to the fourth plus 5x cubed plus 4x minus 7. Okay, so again, we don't need the entire polynomial to determine the end behavior. We only need the leading term. Okay, so we are going to look at negative 2x to the fourth. Okay, the leading term. This is what we use to determine the end behavior. Okay. All right. So let's determine the right-hand behavior. So the right-hand behavior, if you forget, you can always just draw your axis, and this side is the right, and this is the left. And on the right are the very positive numbers. On the left are the very negative numbers. Okay, so let's figure out what's happening on the right. Will our graph be going up or will it be going down? Okay, so if we plug in, so let's do right-hand behavior. Okay, so if we plug in a very positive number into this term, do I end up with a negative result or a positive result? I get a negative result. Okay. Okay. So that means it's going to be going down on the right. Okay. Let's do the left-hand behavior. Okay. So on the left-hand side, all the x's are very negative. Okay. So if I plug in a very negative number in here and raise it to the fourth power and then multiply it by negative 2, what sort of result will I end up with for my left-hand behavior? Plug in a negative, very negative number like negative 1,000,000, raise it to the fourth power. That's going to be positive, and then multiply it by negative 2, and that's going to give us a negative result. Okay, so on the left-hand side, the graph will also be going down. Okay, so the way we write this formally is like this. All right, so for the right-hand behavior, our HB, okay, right-hand behavior. So what we say is as our x values go towards positive infinity, then our y values, or our results, or our polynomial p of x, becomes negative, or goes towards negative infinity. Okay, and for the left-hand behavior, so the left-hand behavior, okay, all the x's go towards the negative infinity, right? So as x goes towards negative infinity, we found out over here that our polynomial goes downwards, so it goes towards negative infinity. Okay, so that's how you write it formally. As x goes, for right-hand behavior, as x goes towards positive infinity, that's to the right, then your polynomial starts to fall, goes towards negative infinity. And we found that out over here. Okay. All right, let's take a look at another example. Suppose that I have this polynomial, p of x equals negative 3x to the fifth minus 2x squared plus x minus 1. Okay, so again, we don't need the entire polynomial. We only need to look at the leading term. Okay, so let's do the right-hand behavior. Okay, and so the right-hand behavior is as x goes towards positive. It becomes more and more positive, right? So when I plug in a very positive number into negative 3x to the fifth, what kind of result do I get? My polynomial becomes negative or positive? You should have said negative. Okay? Because when you plug in a very positive number and raise it to the fifth power, you get a positive result, and then times negative 3 will give you negative. Okay? Let's do the left-hand behavior. Okay? So left-hand behavior, that means that x is going towards negative infinity. That's to the left. Okay, so as x goes towards the left, towards negative infinity, what happens to this term? Well, let's plug in a very negative number, raise it to the fifth power, we get a negative result, and then multiply it by negative 3, and that will give us a positive result. Okay? So on the left-hand side, it will be going up. On the right-hand side, it will be going down. Okay? All right, let's do another one. Suppose your polynomial is written like this. Negative 3x, parentheses, 2x squared minus x plus 1. Okay? So it looks a little different from the other one. This one, we have these parentheses, and the other ones we did not. Okay, so what you want to do is definitely multiply this out. It's just a monomial. It doesn't take too much work. In reality, you really only need to do this one and the leading term. Okay, so we get negative 6x to the third. Okay. And that's all I need. So you could, if you want to multiply the rest of it out, you get plus 3x squared minus 3x. Okay, but I don't need all of this here. So I don't need all of this. I only need that leading term, so you don't actually have to multiply that out. Okay, so I'm going to go ahead and erase that because I don't need these. I only need the leading term. Okay, but I don't want to say they're equal, so I'm gonna use an arrow instead once I can get my pen back. Okay. All right, so don't say equal then if you're not going to multiply it all out. Okay. So we get negative 6x cubed. That's what we're going to use for our leading term. And So let's go ahead and begin. Our right-hand behavior. So that's as x goes towards positive infinity. So as x goes towards positive infinity, x gets very, very positive, right? So as x goes towards positive infinity, let's plug that in. If you want to use positive 1 million, you can. Positive 1 million to the third power is positive, and then times -6. So our polynomial goes towards negative. So on the right-hand side, it will be going down. Okay, so the graph will be going down on the right. And then let's also do the left-hand behavior. The left-hand behavior. So that's as x goes towards negative infinity. To the left is a negative. Okay. So let's plug in a very negative number. So a very negative number to the third power is going to be negative. Times -6 will become positive. So our polynomial goes towards positive. So on the left-hand side, our graph will be going upward. Wait for it. It's going to show up any second now. There it is. Okay. So that's how you do it. Again, you don't need to multiply the entire polynomial out since you only use the leading term to determine the end behavior. Okay, so I'll show you another one like this where it's not multiplied out. Okay, so suppose that I have this one here. P of x equals -3x squared times 5 minus x times 2x plus 1. So just like the previous example, you only multiply the leading term in each of the pieces. So unless you really, really want to multiply everything out completely, you can, but you don't need to. So these are the terms I'm going to multiply together. I'm going to multiply that one with this one, -x, and this one, 2x. Okay. All right. So waiting for my black pen to come back. Okay, so I'm only going to use those. And what I come up with here is -3 times -1 times 2. So that's going to be +6. And I get x squared times x times x. That's x to the 4th. Okay, so that's going to be my leading term. I don't need the rest of the terms. So now I can go ahead and figure out my right behavior. So right-hand behavior, that's as x goes towards positive infinity. Okay, so if I plug in a very positive number, I get a positive result. So positive. So that means on the right-hand side, my graph will be going up. Okay. Let's do the left-hand behavior. Okay, so left-hand behavior, that's as x goes towards negative infinity. So let's go ahead and plug in a very negative number. So a very negative number to the 4th power is going to become positive. And positive times 6 is, oops, that should be an arrow, is going to be positive. Okay. Oops, that got messy. Hold on, let me erase that and write it a little more clearly because my screen moved. Okay. There we go. All right, so this needs an arrow and this needs an arrow. So when we plug in a negative number, we end up with a positive result. So on the left-hand side, the graph will be going up. On the right-hand side, the graph will also be going up. Okay, so that's how you do these. This is how you determine the end behavior. And that's what you'll need to do when we get into graphing these higher degree polynomials. So I wanted you to get used to first determining the end behavior. So that's what this video is all about. The next part, part 2 of 3.2, we'll deal with finding the real zeros of the polynomial, which are the x-intercepts. Okay? All right. Thanks for watching.